Hi, and welcome back to my channel. This thing you see here is the amplifier, which I've been using in my previous videos to amplify the signal coming from a mixer. So the signal was going to the input of the amplifier, and it contains frequencies from very low frequencies, basically 0 to 500 megahertz. And the goal of this amplifier is to amplify only the low frequencies, ideally from 0 to 20 kilohertz, which is the audible voice. And to design this amplifier, I mean, the design is very well known and is basically called the common emitter and common collector amplifiers together. There are two transistors here. So it's absolutely well known, but to experiment, with the precise values of the capacitor, the resistors, and these kind of things, I used a software which is called LTSpice, and this has been very useful for me. So the goal of this video is to illustrate to you how this works, because it's quite easy and it can be very time saving. The idea is that you can try it very quickly in the software if things works, and save a lot of time. The move to the breadboard only when things work, at least in theory, in the simulator. So before moving to the description of the software, let me discuss a little bit about the amplifier and basically the specification. Okay, so what this is supposed to achieve. So at the moment the amplifier is connected to this signal generator coming here. Okay. The input of the amplifier, so basically coming from the signal generator, is going to channel 2 of the oscilloscope. So is this signal here, currently at 100 millivolt, and the output is this larger signal, which is indeed amplified. In fact, is much more amplified. Let me show both of them. Is much more amplified than that. The amplification is quite large. It's about 40 times. So it's not huge, but it's about 40 times larger. Okay. And right. So of course, one of the specification of the amplifier was amplify. Okay. Okay. So it is doing that. The second the specification was to amplify only the low frequencies and not the high frequencies. So let me show you that this is indeed the case. At the moment I have the frequencies of 5 kilohertz. So let me just show you the amplified signal, so channel 1. And if I increase the frequency, you can see that the amplification is going down. I hope this is visible. We are at 30 kilohertz now, and it's clearly going down. If I set it to 1 megahertz, for example, it almost completely disappears. Okay. So the second specification is met. Let me go back to 5 kilohertz. And the third and last specification was that this amplifier has to have a precise 50 ohm input impedance. In other words, we don't want any rejected frequency back to the mixer or to the signal generator in this case. Okay. This was a requirement of the specific mixer I was using, and to work well, it doesn't really want any reflections. And so to see that this is the case, let me switch to just the input. So that's channel 2 here is looking at the input. And if I now move the frequencies, change the frequencies, so let me modify it, we get 30 kilohertz. As you can see, the input is not, the amplitude of the input is not changing when the frequency changes. So this is a sign that indeed the input impedance of the amplifier is 50 ohm. Otherwise it would change with frequency. Let me put 5 megahertz, for example, and as you can see, well, it was slightly a bit attenuated. But that's probably because in the breadboard there is capacitance everywhere. Okay, so high frequencies find a way to ground different than what is expected, but anyway, it's not very much attenuated. So this means that this amplifier is respecting these constraints up to a certain degree of having a good 50 ohm input impedance. So okay, these were the three constraints I had on this amplifier: 1 to amplify, 2 to only amplify low frequencies, and 3 to have a 50 ohm input impedance. And with this said, we'll now move to the software to show you how LTSpice works. Okay, so the software we are going to use is called LTSpice. It's available from this website, analog.com, from Analog Devices. And as you can see, it's only available for Windows and Mac OS. If you are using Linux, like me here, I have Ubuntu, you can solve this by installing VirtualBox, and so you have your virtual machine with Windows installed. Okay, so I have already installed LTSpice 17, as you can see here. I spare you the details of the installation process. And so let me just open it. And so this is the interface that you have. It's very simple. And you can start a new schematic with File, New Schematic. Okay, so this is going to be the board where you draw your schematics. You can have actually several schematics open at the same time. So for example, if I open these schematics here that I already saved before, this contains the schematics of the amplifier that I have been using in my previous videos. Okay, so let me close this for the moment, or rather minimize it. I'm going to start a new project here, a basic amplifier based on transistor here, just to illustrate how LTSpice works and what it can do very quickly. And yeah, this is not going to be an in-depth introduction. It's just going to be a very brief introduction just for the beginners like myself who want to start doing something very quickly with this tool. So the first thing you have to do in a new project is to put somewhere your ground. So this is going to be your voltage reference. Okay, so this is going to be 0 volts around your board basically. And as you can see in LTSpice, when you click something with the mouse and you do something like putting down the ground, the mouse keep having the same icon. So if I click somewhere else, for example here, I'm putting down the ground again. So to turn off this, I just have to push the escape button on my keyboard, and so I get back to a normal pointer. So to delete something that you don't like, just select this cut functionality and you can delete the ground. Here with this pencil we can draw wires. So as you can see, I can click around and draw wires as much as I want, and when I want to stop, I just push the escape button on my keyboard like that. Okay, so I can zoom in, zoom out with the mouse wheel, and then I can add the components. So let me click here, which is the button to add components, and as you can see, there are many things, so pumps, filter, DAC, comparators, whatever, and there is this search functionality. So for example, if I write volt, I get voltage, and so I can place in my draft here in my board a voltage source. For example, I want to place it there. I press the escape button, and if I push the right button, I get to set its DC value. For example, 10 volts, which was the value in my real power supply. Okay, so as you can see, we see 10 volts. The name of the power supply is called V1. So let me change that. Where I can do that, let me see, perhaps here. Yes, okay, instead of V1 I call it power supply. Okay, so I cannot put the spaces in names, fair enough, so I'm going to write something like that. Okay, so I don't like now the name power supply being above this line, so let me just move with this functionality the power supply somewhere else. Okay, like here, perfect. I'm going to connect the power supply minus sign to ground, the negative terminal to ground, like that. And okay, good. And perhaps let me also connect the plus side to this other line. Okay, so this is going to represent our positive rail. Of course, now we have sort of shorted the positive rail to the ground rail by doing that. So let me just eliminate this wire, it's not needed anymore. Okay, perfect. So this was my DC power supply. Let me also add another voltage source. But this represents the analog signal, the AC signal that we are getting from the mixer. So if I select here, as you can see, I can only put the DC value, but if I go to advanced, I can change this voltage source to a sine, so sinusoidal voltage source. Okay, and here I can set its amplitude in the simulation that we will do. So let me put it 0.050, so that's gonna be 50 millivolts, so the value is expressed in volt. And here, since it's a 50 ohm input, I'm going to specify its a series resistance to be 50 ohm. Okay, so we get our thing here. I'm going to connect the minus side to ground. Okay, and okay, fine. So let me draw some more wires. Okay, so this is basically the input we are getting from the mixer, and our goal is to amplify it. So one of the constraints we had from the amplifier was that it has to have a very good 50 ohm impedance, so to be a very good termination. And so a perfect termination, of course, would be something like that, ideally. Just a resistor that I'm putting here. Of course, I selected resistor from there. And this resistor to be a 50 ohm resistor. Okay, so this will be a perfect theoretical termination, an ideal termination. So already with these very simple schematics that we have here, as you can see, it's kind of trivial. We can run the first simulation to see what's going on. So to run a simulation, you click here on this running man, and it allows you to select among several simulations. So let me do AC analysis of linear type. You will see in a moment what that means. I want this to go from 500 Hertz to, let's say, 5 megahertz. Okay, the syntax for megahertz is meg. Okay, so let me do that, and now the simulation has started. As you can see, LTSpice has put this label on the schematics to remind us that this is the simulation under execution. Right, so if I click on some point on the circuit, for example here, I can see what the response is. So as you can see on the x-axis here we have frequencies. So the simulation is simulating for each frequency, here 2 megahertz, here 1.5 megahertz, here half a megahertz, the response. And the response is perfectly flat. As you can see, the response is voltage. Here is measured in dB. So let me change that. Let me change it to linear. So we are going to see millivolts. And as you can see, the response we are reading is completely flat across the spectrum, and it is 25 millivolts. And that is exactly what you expect, because the source here has 50 millivolts of voltage. It has a series resistance of 50. And since the load is also 50 ohm, we get basically a voltage division of 2. So we get our 25 millivolts as an output. And the fact that this is a theoretically perfect load is witnessed by the fact that the response is perfectly flat, okay? So when we see this flat line, it means that the load is perfectly flat. And just to see, for example, a bad load, what that would be, so let me add this, and I'm going to add a capacitor here, a capacitor of, let's say, 0.1 microfarads. Okay, so this is the syntax used. So now the circuit is like that. Let's see what happened to our response. Now it's not at all flat, okay, because this capacitor is going to have a different impedance at different frequencies, and so in parallel with 50 ohm, this will result in a widely ranging impedance. Okay, so that's no good for our purposes, at least. We want a very flat response. So let me cancel this. And let me just basically lay out the schematics for my amplifier based on a transistor. So it's an NPN transistor. I'm going to put it there. So let me do a couple of things. So the goal of this video is not really to discuss the theory of these amplifiers. It's not something I'm inventing. This is called a common collector amplifier. So let me just lay down quickly without explaining too much how things works theoretically. I just want to discuss here the LTSpice simulation software, not the design itself. And so let me connect these points. All right, so there is a broken wire there. Okay. And what else? I want to place a capacitor here, but as you can see, the capacitor is vertical. I want it to be horizontal, so I can type Ctrl R, and then I get the rotation I want. So let me place it here, for example, and then I have the connection here. Okay, so now we have a good connection. So let's set some values. So I think here what should okay, so let me stop so okay, so here it's asking me, so wait a second, how can I stop this simulation like that? Probably. Okay, so now I can edit the value of the capacitor, I guess. So what's going on here? I have some problem with this, so I'm not okay, right, I'm not sure the pointer was not working properly. Anyway, let me set the capacitor value. So I think I use in my breadboard 330 microfarads. Here, if I remember correctly, I use 5 kilo ohms, and here I used let me see, 1 kilo ohm. I can also write 1K for 1 kilo ohm, okay? And so the output of this type of amplifier, of this configuration of the transistor, is read here. So let's see how if it is working. So I'm going to run, I execute the simulation. And so here we get our input signal. As you can see, well, let me put again here the linear scale, so millivolts. It's pretty flat, okay? It's pretty flat across the spectrum, so from 0 to 5 megahertz. We're getting our 25 millivolt response. If you're wondering what these dots are, this is the phased measure in degrees here. And so as you can see, the phase is very, very close to 0 degrees, which would be at a perfect response. So that's completely fine. It's a flat response. So the input is at 25 millivolts. I mean, it's really at 50, but we are reading 25. Let's see what the output is. And the output is at 4 microvolts. So really the transistor on the moment is not amplifying anything. It's not working. And this is because we are missing some voltage here. So let me add that by means of a voltage divider. So I'm going to add 2 resistors, and the values here, if I remember correctly, were something like that. Okay, so let me run again the simulation, and let's see now what's going on. So here I have my 25 millivolts, and here I should see now something. No, it's still not working for some reason. Let me try to understand what's going on. So okay, I don't know what's going on, so I'm going to change now the type of simulation to understand what's going on, and I'm going to edit the simulation and not do an AC analysis anymore. I'm going to do a DC analysis. So it's this one. As you can see, I have to drop this new analysis somewhere on the schematics, and let me run it. Okay, so this is the result. You don't need to read it here, because you can simply select a point in the diagram, in the schematics, and this will give us the corresponding, so if you, in the bottom left part here, we can read values. So for example, on this point, there are 414 millivolts. Okay, so that's a bit weird actually, because here we have 10 volts, right? And so here the voltage division should give us a slightly different value, should namely give us 1.7 volts. Isn't it that right? So so let's see. Here we have 10 volts. Here, yeah, 1.7 volts. Okay. So you see, we discovered the problem. So let me delete. So that can be a bit tricky. Let me zoom in a little bit. Okay, so anyway, this was useful to show a point that you can use simulation to see what's going on. So if I measure here, I can see correctly 1.7 volts on the bottom left part, okay, here. You see? This is what I was expecting because I'm dividing, basically this resistor is determining the value because it's a voltage divider. And here, instead, I'm reading 414 millivolts. How is it possible if these are connected? Well, the answer is that these are probably not connected due to some, well, I don't know, whatever reason. So let me connect them again, so to make sure that, okay, now they are connected. So let me run the analysis again. And here you see now we get our expected 1.78, or more or less 1.7 volts, which is great. So let me zoom out again. And let me run again the AC analysis. So again, I change the simulation, I go back to AC analysis, and let me start it again. So here I have my input at minus 32 dB, which means, as we know, 25 millivolts. And the output is here. Let's have a look. And it is minus 18 dBs. So let's see what this means in millivolts. It is 118 millivolts, so we amplify the signal almost by 5. And indeed, this is the two resistors here in this type of configuration of amplifier determine the gain. So the gain is 5 divided by 1000, which is about 5, and that corresponds to what we are seeing here. Let me change again to decibel notation, which is more handy. When we want to compare two things that are very different. So here we have our input, and here we have our output. Input in green and output in blue. Okay, so this is the amplifier is almost finished. However, it's not meeting all our constraints. Namely, as you can see here, there is this 5 kilo ohm resistor. And so the source of this amplified signal has a very high impedance. And so, for example, if I decide to drive with it directly a speaker, so let's simulate that. We can model the speaker as a resistor of, let's say, 600 ohm. So let's put this here. And let's see what's going on in the simulation. So again, we have our input in green, stays the same, and the output has collapsed to minus 36 dB. So we are not amplifying, we are decreasing the signal, in fact. And this is because this load is too low. I mean, the resistance of this load is too low compared to the input impedance resistance of the amplifier. So we need another stage to fix this problem, and let me do that quickly, or rather let me just show you the final circuit I came up with. Now you can see the full schematics here, and it is this. So again, we have our voltage source. This is exactly as before, so we get our amplification with a high impedance, and then we use another transistor. In this configuration it's called a common emitter amplifier, or also a voltage follower, and the difference, as you can see, is that there is no resistor here, so the impedance is very low, and this allows us to drive the speaker, this 600 ohm resistor. So let me run the simulation to see that. So here we get minus 26 dB. So it's not what we had before, because here, as you can see, we are not emitting a 50 millivolt signal, but a 100 millivolt signal. So let me actually change that so we can have the same readings that we had before in the simulation. Okay, so run again. So again, we get our minus 32 dB here. This is the input. After the first stage of amplification, we get a much higher signal, amplified by a lot, almost, how much is that? Almost 40 dB. And this is because here I tweaked around with the resistors. So the trick is to use, to increase the gain, is to have another resistor in parallel with the other one, with a capacitor. I'm not going to discuss why this is the reason, but if you study the common emitter, common collector amplifier configuration, you will discover why this is the case. And finally, let's see what is the output. And the output here is exactly as in the first stage, but as you can see, is not affected by the load of the speaker. This is called a common emitter amplifier, so the input, which is here, and the output, which is here, are exactly the same. Excellent. There is only one thing here that I have not discussed, is this capacitor. This capacitor is to create some kind of a low-pass filter dynamics in this type of amplifier. So if you see here, we are sweeping from basically 0 to 50 kilohertz. But if I can modify that, so we sweep from instead of 5 kilohertz to, let's say, 5 megahertz, we are going to see a big difference. So the signal is greatly amplified at low frequencies, but as you can see, by the time we reach, I don't know, 400 kilohertz, is not amplified anymore, and then for higher frequencies we go down and down, and this is thanks to this capacitor. This is what we wanted, because we only wanted to increase audio frequencies and not much higher frequencies. If I, for example, remove this capacitor, you will see what the difference is. So let me run again the simulation. And as you can see, we are now also amplifying higher frequencies. Okay, so let me edit and undo that. So the capacitor is there again. Let me run again the simulation, and then we get our desired result. So as you can see, LTSpice is great to quickly simulate things and see the behavior of little changes. So for example, suppose I don't have exactly 8300 ohm resistor. Let me put it 12K resistor. Let me see how this affects things. Not so much, okay? So I can be confidently replace my 8.3 kilo ohm resistor with a 12K resistor without fearing too many problems. And in general, it's great to be able to very quickly check if things work without spending a lot of time on the breadboard. Another problem with the breadboard is that it is not a perfect scenario. You know, every component has some capacitance and you know, in fact, a lot of capacitance in a breadboard. So sometimes you don't get the results that you want. Very often it is because the circuit is simply wrong. But sometimes it's because the circuit is, I mean, you get the correct behavior in theory, but in practice, due to many imperfections like capacitance or, you know, these type of things, it's not working as you expect. So sometimes it's good to understand if something works, at least in theory. And then if it doesn't work in practice, at least you can try to understand what is the difference between the theory and the practice. So for example, just to give you an example, suppose that here the resistor is not a perfect resistor. Suppose it has, for example, it is a 51 ohm, or rather 52 ohm resistor. Let's see what happens. Not much, as you can see, but suppose this resistor has also some capacitance. Okay, so let me put in, I can model this as a parallel capacitance here, and so let me put just let's say, I don't know, 2 picofarads of capacitance. Okay, this might be a realistic resistor with some capacitance. I don't know why. In a breadboard anyway, everything has capacitance, so that could be realistic. So that does not affect too much the results. So let me increase the capacitance, I don't know, to 2 nanofarads, so it's much larger. Now, as you can see, things are starting to change a little bit, but not dramatically. Okay, so anyway, you can experiment with these scenarios on the simulator, and I think it's a great way to make experiments quickly and to understand what's going on. Okay, so this is all for this video. If you have any questions, please just leave a comment in the section below, and I'll see you next time. Bye bye.